Today we'll discuss about the mathematical induction. We will use the mathematical induction to prove the statement 1 plus 2 plus 3 so on up to n is sigma n, which is equal to n into n plus 1 by 2. Okay, so s of let Sn 1 plus 2 plus 3 so on up to n equal to n into n plus 1 by 2. N into n plus 1 by 2. So step number 1. Step 1, we will prove for n equal to 1. We will prove S of 1 is true for n equal to 1. So left hand side 1 is there. The first term right hand side n into n plus 1 by 2, 1 into 1 plus 1 by 2, 1 plus 1 is 2 by 2 is 1. So left hand side equal to right hand side. Therefore it is true for n equal to 1. Therefore S of 1 is true for n equal to 1. Step 2. Step 2. We will assume that S of n is true for n equal to k. For n equal to k is greater than n. That means 1 plus 2 plus 3 so on up to k equal to k into k plus 1 by 2. That is step 2. Step 3. Step 3. We will prove that S of n is true for n equal to k plus 1. So that means 1, 2, 3 so on up to k into k plus 1 by 2. So this is k, n equal to k plus 1. So n equal to k plus 1. So here extra we are writing k plus 1. Here also k plus 1. Okay. So now this is right hand side k into k plus 1 by 2 plus ka plus 1. So here in both the terms k plus 1 is common. So this is k by 2 plus 1. So this is k plus 1, k plus 2 by 2. Therefore it is true for n is equal to k plus 1. Hence by principle of mathematical induction, S of n is true for all values of n. So what we have done here? Three things we have done. What are the three things? We showed that it is true for it is true for n equal to 1. Then we assume step number 2, we assume that it is true for n equal to k. Now we want to step 3, we have to show that it is true for n equal to k plus 1. So adding k plus 1 both the sides, then after that simplifying, you see n into n plus 1 by 2. So n equal to k plus 1, k plus 1, k plus 1 plus 1 by 2. Hence, by principle of mathematical induction, it is true for all values of n belongs to natural numbers. One more problem. We'll go for one more problem. Induction. Summation k equal to 1 to n 2k plus 1 whole square into n2 into 2n minus 1 2n plus 1 by 3 for all values of n belongs to natural number. You see, we have to prove by mathematical relation. So this is 1 square, 2 square, 1 square plus 3 square plus 5 square, so on up to 2n minus 1 square equal to n into 2n minus 1, 2n plus 1 by 3. Okay. Now it's step number 1. What is step number 1? N equal to 1. We have to take to prove this, we are calling S of n. To prove that S of n is true for n equal to 1. So left hand side 1 square is 1. Some teachers they take this number also and take equal to 1. So now right hand side n equal to 1. 2 times 1 is 2. 2 minus 1. 2 times 1 is 2. 2 plus 1 is 3 by 3. 2 minus 1 is 1. This is 1. This is 3. 3 3 getting a 1 into 1 is 1. So left hand side is also 1. Right hand side. So left hand side equal to right hand side. Therefore S of 1 is true for n equal to 1. Now what is our step 2? Step 2 is we have to assume that assume that S of n is true for n equal to k and k is greater than or 1. So that means S of k equal to 1 square, 3 square, 5 square, so on up to 2k n minus 1 whole square equal to k into 2k minus 1, 2k plus 1 by 3. This is step 2. Step 2 is just we are assuming. Step 3 we are proving. What we are doing to prove that S of n is true for n equal to k plus 1. That we have to prove. So let me write down here 1 square, 3 square, 5 square, so on up to k minus 1 whole square equal to k into 2k minus 1, 2k plus 1 by 3. What we have to do? We have to prove it is true for n equal to k plus 1. K plus 1 means the series in the form of two odd numbers, 1 square, 3 square. So the next 2k minus 1, the next term will be 2k plus 1 square. 2k plus 1 square. Adding 2k plus 1 both these sides. So now right hand side, this part 2k plus 1 whole square. This is 2k plus 1. I am taking common. So this is 2k into k minus 1 by 3. And this is 2k plus 1. Because 2k plus 1 common you have taken. So this is 2k plus 1 outside. Now we have to simplify this. 3, if you multiply 2k square minus k, this 3 will go here. 3 2 is 6. 6k plus 3. 2k plus 1. 3. 2k square minus k plus 6k is 5k plus 3. Now see here. 2k plus 1. This one. If you make the factors, it will be k plus 1, 2k plus 3, all divided by 3. So this comes k plus 1 into 2k plus 1 into 2k plus 3 divided by 3. This we are making the factors. These factors. If you make the factors, you will get these two factors. So now it is in the form of n equal to k plus 1. You see, this is n, this is 2n minus 1 form, this is 2n plus 1. Adding n equal to k plus 1, k plus 1, k plus 1. Therefore, by the principle of mathematical induction, S of n is true for all values of n belongs to natural numbers. One more problem of this type, different type. Show that for all values of n belongs to natural number, 1 by 1 into 4 plus 1 by 4 into 7 plus 1 by 7 into 10, so on, up to n terms equal to n by 3n plus 1. Here this problem, we don't have n term of this series. So first terms we will take 1, 4, 7. Then get second series we will take 1, 7, 4. So let me take the first series 1 plus 4 plus 7, so on. A equal to 1, common difference t2 minus t1. t2 minus t1. What is the n term of the series? Tn equal to n minus 1 into d. So n term will be a is 1, n minus 1. So it is 3n minus 2. And the second is the blue one. 4, 7, 10, so on. Your A is 4, D is T2 minus T1 or 10 minus 7, 3. So Tn formula is A plus n minus 1 into the A is 4, n minus common difference is 3. Common difference is 3. So this is 4 plus 3n minus 3 or 3n plus 1. So therefore, the n term is Sn equal to 1 by 1 times 4, 4 times 7. So what is our n term? 3n minus 2, 3n plus 1 equal to n by 3n plus 1. Now the problem in into the shape. Now we'll go for the first step. Now n term we have. Previously we don't have n term. So we have to find up to n term it is given. So we need to find n terms. Now it is here. Now Sn equal to this thing. The first step what we have to do? We have to prove for S of n is true for n equal to 1. So what is our left hand side? 1 into 4 is 1 by 4. So right hand side n equal to 1, 3 plus 1 is 4. So left hand side equal to right hand side. Step number 1 is over. Now step number 2, we have to assume. Let us assume that S of n is true for n equal to k. So 1.4, 4.7, so on equal to 1 by 3k minus 2, 3k plus 1 equal to k by 3k plus 1. This is the assumption. Now we have to prove step 3. To prove that S of n is true for n equal to k plus 1. So k plus 1 term, k plus 1 term will be 1 by, wherever a k is there you have to write k plus 1. So k equal to k plus 1, k plus 1. So 1 by 3k plus 3k minus 2 is 3k plus 1. This is 3k plus 1 is the plus 3 plus 1 is 4. 3k plus 4. This is k plus 1 term. So next 1 times 4, 1 by 4 by 7, 3k minus 2, 3k plus 1. Now we have to add k plus 1 term. What is k plus 1 term? 1 by 3k plus 1, 3k plus 4 equal to k by 3k plus 1. This is k plus 1 term. 1 by 3k plus 1, k plus. See here, this is the part extra we are writing. Both the side of the equation to balance. Because this is k plus 1 term, this is k plus 1 term. Now we have to simplify this right hand side. K by 3k plus 1, k by 3k plus 1 plus 1 by 3k plus 1, 3k plus 1, 3k plus 4. So 1 by 3k plus 1 if I take, so we are left with k 1 by 3k plus 4, 3k plus 4. So 3k plus 1, if you take the LCM, 3k plus 4, this is k into 3k plus 4 plus 1. So this will be 1 by 3k plus 1. This is 3k square 4k plus 1 divided by 3k plus 4. 3k plus 1, 3k plus 4. This is 3k square factors. 3 and 1 is the factor. So 3 plus 1 is 4. We want 4k. So both should be in addition. 3k plus 3k plus k plus 1 divided by common we have taken outside. So this is 3k if you take common, k plus 1, 1. So now 3k plus 1, this k plus 1 is common, divided by 3k plus 1, 3k plus 4. This is gone. So k plus 1 by 3k plus 4. So therefore this is the sum form. N by, what is that formula? N by 3n plus 1. You see, n equal to k plus 1. N equal to k plus 1. So k plus 1, 3, 4. So therefore, S of n plus 1, k plus 1 is true. Therefore, by the principle of mathematical induction, if S of n is true for all values of n belongs to natural number. The problem is little bit big, but it's the easy one. Only 3 steps are there to prove. One more problem, different type. Problem number 4. What it says? Prove by mathematical induction 1 into 2 into 3, 2 into 3 into 4, so on, up to n terms equal to n into n plus 1, n plus 2, n plus 3 by 4. See here. This is the first 1, 2, 3. Then this is the second one. 2, 3, 4 it will go. And this is the third one. 3, 4, like that it will go. So now 1 is 1 plus 2 plus 3. So on, so on. So here A equal to 1, common difference is 1. So Tn equal to 1 plus n minus 1 into 1. So it is just n. Now if we go with the second one is 2, 3, 4, so on. Your A is 2, D is 1. So Tn is A plus n minus 1 into D. Difference is 1. So n plus 1. Similarly, if you go for the third one, 3, 4, 5, A equal to 3, D equal to 1. So Tn equal to 3 plus n minus 1 into 3. So n plus 2. So n plus 1, n plus 2. So the series will be 1 into 2 into 3, 2 into 3 into 4, so on. N term is n into n plus 1, n plus 2 equal to n into n plus 1, n plus 2, n plus 3 by 4. Now the problem is in the standard. Now we have to go for the step number 1. There are 3 steps to prove. First step number 1 is to prove that the given statement is true for n equal to 1. Prove that this we are calling as S of n. Prove that S of n is true for n equal to 1. So left hand side 1, 2, 3, 1 into 2 into 3, 1 2 are 2, 2 3 is 6. Right hand side 1 into 1 plus 1, 1 plus 2, 1 plus 3. 1, 1 plus 1 is 2, 2 plus 3, 3 plus 1 4. By 4, 4 getting a 2 times 3 is 6. Therefore, left hand side equal to 6 equal to right. So that means it is true for S of 1. S of 1 is true, or it is true for n equal to 1. Now step 2, we have to assume. Step 2, assume that S of n is true for n equal to k. That means 1, 2, 3, 2, 3, 4, so on, k into k plus 1, k plus 2 equal to k into k plus 1, k plus 2, k plus 3 by 4. What is step 3? Step 3 really we are doing only in the step 3. Step 3, to prove that S of n is true for n equal to k plus 1. So k plus 1 term will be, what will be the k plus 1? ID you have to add. K will become k plus 1. K plus 1 will become k plus 2. K plus 2 will become k plus 3. This is the k plus 1. So 1 into 2 into 3, k into k plus 1, k plus 2. k into k plus 1, k plus 2, 3 by 4. What is the term? K plus 1 term? K plus 1, k plus 2, k plus 3. Here also you have to write k plus 1, k plus 2, k plus 3. Now this part, the blue part, first let me write down the blue part. K into k plus 1, k plus 2, k plus 3. Plus the red part. Red part is k plus 1. So what is the extra part? K plus 1, k plus 2, k plus 3. This part if you take, only k is left. And this is by 4 is there. So k by 4. This just 1 is left. So this is k plus 1, k plus 2, k plus 3, k plus 4 by 4, or k plus 1, k plus 2, k plus 3, k plus 4 by 4. So therefore S of k plus 1 is true for n equal to k plus 1. Therefore by the principle of mathematical induction, S of n is true for all values of n belongs to natural number. That's it. Next, one more problem of different type. Problem number 5. Show that for all values of n belongs to natural number 1 square, 1 square plus 2 square, second term, third term 1 square plus 2 square plus 3 square, so on, up to n terms equal to n into n plus 1 whole square, n plus 2 by 12. Okay. So we have to prove by mi, all problem by mi only. So 1 square, 2 square, 3 square, n square equal to n into n plus 1, 2n plus 1 by 6. So step 1, to prove for Sn n equal to 1. So left hand side equal to 1 into 1 plus 1, 2 plus 1 by 6. 1 plus 1 is 2, 2 plus 1 is 3, 6 by 6 is 1. Now right hand side, 1 into 1 plus 1 whole square, 1 plus 2 by 12. 1 plus 1 is 2, 2 square into 3 by 12. 2 square is 4, 4 into 3 is 12, 12 by 12 is 1. So left hand side equal to right hand side. Therefore, S of 1 is true for n equal to 1. Step number 1. Step number 2, assumption is there. We are not doing anything, just we are assuming. Step number 2, let us assume that S of n is true for n equal to k. So that means 1 square plus 2 square, 1 square plus 2 square, 3 square, so on is equal to k into k plus 1, 2k plus 1 by 6 equal to k into k plus 1 whole square, k plus 2 by 12. Step 2 is just the as Step 3 we are doing a lot to prove that S of n is true for n equal to k plus 1. So k plus 1 term. So wherever k is there, k plus 1 we have to write. So let me write it down. 1 square, 1 square plus 2 square, 1 square plus 2 square plus 3 square, so on into k plus 1, 2k plus 1 by 6 plus k plus 1, k plus 2, 2k plus 3 by 6 equal to k into k plus 1 whole square, k plus 2 by 12 plus this part, k plus what part, k plus 1, k plus 2, 2k 2k plus 3, 2k plus 3 by 6. Okay. So now right hand side, this is k into k plus 1 whole square, k plus 2 divided by 12 plus k plus 1, k plus 2, 2k plus 3 by 6. So this is equal to, this we can take k plus 1, k plus 2 by 6 common. This k plus 1, k plus 2 we have taken. So k into k plus 1 by 2. And this 6 you have taken common, k plus 1 you have taken common, k plus. This will be let's try 2k plus 3. 2k plus 3. Okay. So now k plus 1, k plus 2 by 6. This if you take LCM, 2 will be there. This is k square plus k. This will be, LCM is 2, so 2 to the 4, 2 3 is a 6. Again k plus 1, k plus 2. This 2 and 6 is 12. So we are left with k square plus 5k plus 6. Now k plus 1, k plus 2. If you take the factor of 5 is 2 and 3. So k square plus 2k plus 3k plus 6. This one pair, here taking k common, here taking 3 common. So k plus 1, k plus 2 by 12, If you take k common, k plus 2. If you take 3 common, k plus 2. Again k plus 2 common, k plus 3. So this will be k plus 1, k plus 2 by 12, k plus 2, k plus 3. So this is k plus 1, k plus 2 square, k plus 3 by 12. Therefore, k plus 1, s of k is 2. Therefore, 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 by principle of mathematical induction, s of n is true for all values of n, for all values of n. So there are three steps. One step is n equal to 1. Second step is we have to assume that it is true for n equal to k. Third step, if we are able to prove it is true for n equal to k plus 1, hence by induction it is true for all values of n belongs to natural numbers. So only three steps are there. N equal to 1 we have to prove. Step 2, we have to assume it is true for n equal to k. Third step, we have to show that it is true for n equal to k plus 1. Hence, by induction, it is true for all values of n. Suppose if n term is not there, you have to find the n term. Which series? It may be arithmetic series, geometric series. You have to find the n term. Again, you have to proceed. I have shown all the methods, all the types of mathematical induction. Okay, thanks for watching. I am making one more video for mathematical induction. Please subscribe my channel. Thanks for watching.